Welcome to the part 2 of the Lab 7 video tutorial. So till now we have completed the part 1, that is we have calculated ln by t and we have verified the result using the test bench. And so while checking the functionality, we have looked into this master slave concept, we have looked into the validity handshake, and these both of these concepts are very useful for the further things as well. So now in the next part we need to calculate the under root ln n divided by t. So till now what we have done, we have calculated ln n divided by t, and next we need to calculate the square root of this thing. So for that I need to add the square root IP, again the floating point IP with the functionality of square root. Okay, so there is the square root. So whatever data that will be put on to this port A, so the square root IP will calculate the square root of that data and will give it. So let's name it as a square root. Precision of input, that's fine, simple precision. So again, no DSP slice is being used for square root calculation. So we will be using the minimum latency. We have to set the A reset. Okay, so while this is getting synthesized, let me make a few changes. So right now I have connected it to the Q port. So I have to change that. So instead of Q ready, I'm connecting it to some intermediate wire. Because now the Q interface will be connected to the square root output of ln n by t. So that's why I'm just connecting it to some intermediate wire rather than this thing. Alright, so that change we have made. Now next thing is to instantiate the square root IP. So for that, let me go to the sources. So as you can see, I have not closed the simulation because I will be using the same wave window for this calculation, because that's the same results which I need to see. So let's name it census QR. So the data that I need to supply is this. And finally, I'm connecting it to the Q interface. Alright, now I can save it. Let's look into hierarchy now, how it's going. Yeah. So these are the conversion from fixed to float, then logarithmic calculation for ln, and then ln by t, and finally the square root. So I have connected the Q interface to the output of the square root IP. So as the simulation is running currently, I can use the same test bench, and I will just relaunch the simulation for the same thing. Right. So let's wait for a while till this simulation gets completed. All right. So we have get the result. As you can see, for ln n by t, we were getting something around 2.3 or something. Yeah. So the square root value is coming out to be 1.51. So we can again verify it using the calculator. So this was ln 100, 4.6 divided by 2 is coming out as 2.3. So next we have, so if we have taken the square root, I can see I'm getting 1.5174. Okay, so that looks good. So I'm getting again till 5 decimal point, I'm getting the correct result. So that is fine. Again, the thing that we need to look for is the valid and ready handshake. So again, the same thing is happening. The IP have put the results, it have put the valid signal. From the test bench, we have set the ready signal, and once the handshake have taken place, the Q valid goes 0. Right? So this was the part 2 of this lab. Now let's move on to the part 3 of the lab. So for this, I will just close the simulation because I will be using X, so it will be better if we get the X in the next window. Meanwhile, let me make some changes in the top underscore Q function. So till under root ln t by t we have calculated. The next thing is we need to do x by t plus the root function, whatever we have calculated. So we have to instantiate the divide IP again, right? So let's do that. So again, I have to connect it to some intermediate wire, the root. Okay. So here's root underscore value. So next thing is to instantiate the division IP again. Okay. So this time this is x divided by t. Okay. Just go ready and together. Okay. So for this x division t, so we have to perform x by t. So my a is the x variable here instead of ln. That is the floating point representation of fx. So the x is x underscore ready, fx underscore valid, and the b part here is, so as you can see, so this t underscore ready signal, if I look at this tft underscore ready, so this was the output from the IP from the slave port. So when we did this ln t by t, so if I look at here, I have connected this ft underscore ready wire to this output port as well, and to this output port as well. So this will create an issue if we do the synthesis of it. This is also known as the multi-driven error. So now in order, although we are not synthesizing it, but it's always a good practice to get rid of this multi-driven thing. So as I can see, this is not actually an input to the IP. It is actually the output which is coming from the IP, and from the simulation waveform I have already seen. So after every clock, so once the result have been delivered, my IP gets ready. So we really don't need to connect it. So what we can do is we can just simply connect comment this thing, and this fx and ft underscore uh, yeah. So this ft underscore valid and ft is fine. This needs to be here. Next, the results needs to be connected to these wire. That's all right. So now we have calculated x by t. Now we have calculated the square root function as well. Now let's do the addition of these results and find and get the final answer out of it. So for that, again, I have to go to IP catalog and get the IP for the addition operation. So now there is a catch in the addition operation. So you can see there is add and subtract. There are multiple options here: multiply, reciprocal, square root. So add, subtract is there. But as you can see, so this add or subtract operation, as you can see, so if you select this add slash subtract, there are two options. Like the one thing is when you select this add slash subtract option, so if I don't select this, let's say I select both, right? So if I select both of them, I'm getting an additional port that is s underscore access underscore operation, right? So that means this IP is capable of performing add or subtract both the operation, but the operation needs to be defined using the operation port. So this is a new thing. So there is one option is that you can simply select the add, and one option you can select the IP for both the operation, add or subtract both, and you can then give the operation from the operation port. So I'm just selecting this the both option for it, right? So I'm selecting the both option so that we will be very clear about it. So not only the add or so the operation port is, if you can see the width of the port, it's an 8-bit port, right? So it's an 8-bit port. So there are different inputs for it that can be given to it. So there are predefined values of those input. Using those input values, you can perform different operations from this single IP, right? So in order to give you a gist of how this thing is working, I'm just taking both operations. You can also take either add or subtract. If you want to do the add operation, you can just select the add operation. That's fine. That's also fine. And naming it as an addition IP. Okay. Precision of input is fine. So as you can see, there is a full usage of DSP slice. So there are multiple operations taking place in this IP. So definitely this DSP thing is needed. So again, the latency I'm selecting is 1. Selecting the A reset time. Okay, now let's instantiate this addition IP. So this operation port here was not needed, but I just added it just to show you how does it works. I'm naming this as result. Alright, the first thing I need to give, that is my x by t. For the b part, I need to give the root function. right? Now here comes the operation. So for the addition, if you look into the documentation of this floating point IP, so for the addition, I can give for the addition, if I want to perform the addition operation from this IP, so on the operation port, I need to provide 0, right? So as it's an 8-bit port, I have to provide 0. Also in the valid, once I provided the 8-bit 0, I can constantly set it to 1. So this ready, again the ready is coming from the IP. So again, it's not very necessary that I may connect it to some wire and I can simply comment it. That's up to me. Right? Next is so the final result should be coming to the queue interface. All right, so that's all that needs to be done for the part 3 of this lab. So now from after the addition, we will get the final result, that is x by k plus under root ln n divided by t. So now once I have saved it, let me run the simulation and check if I'm getting the correct result. So my correct result should come around 2.51, right? Now let's see if I'm getting the correct result or not. That's fine. Let's run the simulation. So the same test bench is fine for this thing. So let's run the simulation and wait for a while till the simulation is completed. And let's check the result. All right. So we have got the results. Now let's rearrange these terms to get a better understanding. X valid and X ready. So T valid and T ready. And finally Q valid and Q ready. Right, so now let's convert it into some desired radix. Okay. Single precision. Alright, so now I'm getting a result 2.51. So if you see, earlier I was getting 1.51, that was the square root function which I was getting. So in that I have added x by t. So I have taken x and t, both has 2 and 2. So that means my result came out to be this thing, right? 1 plus 2.51, so this is 1.2.5174. So the results is fine. Again, so if I look at the handshake, so for the X signal, now as I can see the ready, so the ready is always high from the IP, so IP is always ready to do the computation. And again, as you can see the handshake here, so the data has been put on the Q bus, and then we have got the Q underscore valid signal from the IP, and finally we have set the Q ready for 1. And once the Q valid comes, I have kept this Q underscore ready as 1 for one more clock cycle, and after that I set it to 0 in the test bench. So the Q valid again went to 0. So there is one handshake, this is the handshake, this is again a handshake, this is the handshake, so this is the handshake. So that is the part 3 of this lab. Now one more thing that we can do is, let's test our IP for multiple inputs. So right now what we are doing, we are giving just only one input. So next thing what we can do is we can give multiple inputs. So let's see. It's easy task. All right. So this was, let's take it as 200. So again, after once this thing have done, after 15 nanosecond delay, I'm just changing the n, and similarly this valid signal is getting generated. So let's keep it at 50 nanosecond. So this time let's keep this as 2, but I will change x to, let's say, 4. All right, so this is fine. just copy pasting it, nothing new has been done. So next 50. So let's take axis 4 this time. So instead of adding 1, I'm adding 2. So I should get 3.51 is the result for the next, not the 3.51. So now ln is also changed. Let's do one thing. It's okay. It's fine. So again, I've just copy pasted the first set of input. Just change the input. The rest of the things remains the same. So let's save it and rerun the simulation. So as you can see, the delay is same. The 15 nanosecond delay here, 50 here, and 50 here. So that's fine. So I have saved it. So now let's relaunch the simulation. So meanwhile, this is, so we can calculate what should be the result, right? Okay. So ln 200, this is 5.29. It will be divided by 2. Will get me 2.61, and then I will take a square root. So this is 1.62, right? 1.627, and in this I am adding 2. So I should get 3.627 as the answer. So let's see if I am able to get this answer. So let's wait for the simulation to complete. Alright, so I've got the results. Let's see if the results are fine. So for the first set of data, I have provided 100, 2 and 2. So I was getting 2.51, that was fine. So for the next set of data, so from here, the next set of data changed. So I got 200, I got here I've got 200, and then here I've got 4, and then here I have got, this remains the same, that is the 2. So that's not an issue. So finally I got a result here. So as I see, I got a Q valid signal here, right? And the result is 3.62762, as you can see, 3.62762. That was supposed to be the result because x was 4 this time, so x by t was 2. So 2 plus this quantity should be the result. So as I can see, I'm getting the correct result, right? So that was for the multiple inputs as well. Right, so in this lab, what we have learned about AXI stream. So we are using AXI stream protocol in this thing because there is no address phase. There is no storing of data. The data is streaming from master to slave. That's it. Secondly, we looked into the use of floating point IP and how to use different operations for our purpose. And then we looked into the valid ready handshake. So that's all for lab 7. So we have done all the 3 parts, and we have looked into all the aspects of AXI stream and this valid ready handshake. So that's all for lab 7. Thank you very much.